All right, good evening everybody and welcome to Analog Electronic Circuits. This is lecture 39. So, in the last class we were looking at going over pretty much all that we did with MOS transistors. We were doing it with bipolar transistors, and the first thing, we were looking at the voltage controlled voltage source, that is the common collector amplifier, and there is a small departure from the MOS transistor case, because the input current in the base is not 0. So, consequently, the input impedance of the common collector amplifier is not infinity, right. It is some large value, but it is not infinite. Likewise, if you do the voltage controlled current source also, it is the same story. The input impedance should have been infinite, but in reality it is not. Then moving on, this is the small signal equivalent of the current controlled voltage source. So, yeah, the output voltage will be, assuming that the GM of the transistor is infinite or very large, what will be the incremental output voltage? It is simply IN times R, okay. And this is the trans impedance amplifier. Okay. And finally, we have the current controlled current source, and analogous to the common gate amplifier, we now call it the common base amplifier, and this is the input current source, right, and what will be the output current? Yeah. So, if beta was infinite, like in the MOS, if beta was infinite, then we have exactly the same equivalent as the common gate amplifier, and therefore the output current will simply be equal to IN, right. Now, a small fraction of that input current goes out through the base, and that basically, so what comes out is beta by beta plus 1 times IN, and remember that beta by beta plus 1 is defined to be this quantity alpha. So, alpha is understood, one way of defining alpha is basically the current gain in the common base configuration. Now, like in the MOSFET case, the true transistor, ideally the output characteristics are IC versus VCE, right, for different values of ideally VBE, right. But remember that what do you call, the current is so sensitive to VBE because exponential, right. So, rather than control VBE, people find it easier to control IB, right. So, these are plotted for various values of IB, and so this is the this is the 0.65 volts VCE minimum, and so ideally the curves must be flat, right. So, the collector current in the active region is independent of VC, right, but in reality, well, and this is grossly exaggerated, but I think you get the idea. Right. So, the current is like that. So, like in the MOSFET case, the collector current is Is e to the VBE by VT times, we could have written 1 plus lambda VCE, right, but historically the fellow who first came up with this equation basically said it is VCE by some VA, right, and VA is called the early voltage after the person who came up with this first, right, and VA is basically analogous to 1 over lambda. Okay, lambda's units are per volt, VA's units are volts. So, therefore, the model for the transistor is actually this beta over GM, and beta over GM is often called R pi this is GM, VBE, this is RO. Okay. And it also turns out that there is actually a very large resistance between the base and the collector, right. That also results in some Y12, which is again undesired and actually is very small, but for most practical calculations people just neglect that because the this becomes that resistance is very large and it messes up calculations big time. So, we just move with this. Okay. So, this is the NMOS transistor, and for as far as swings are concerned, the cutoff condition is what is the cutoff condition in the NMOS for the NMOS transistor? IDS, the drain current was 0, now the collector current is 0. And likewise, so the BJT going into saturation, what is the condition? Pardon? I mean, VCE minimum is 0.65 and VBE nominal is 0.65. So, what is that in English? What does that mean? The collector can go as, not up to, as low as the base, right. So, in a MOS transistor, the drain can go one threshold below the gate, whereas in a bipolar transistor, the collector can go as low as the base. So, VCB equal to 0. Okay. So, I mean again as usual, if you see a big big circuit, well the procedure is very straightforward. You first find the operating point, replace every transistor with its incremental equivalent, and what do you call do the small signal analysis. Then then you can find the total voltage everywhere, the total current everywhere, and then to find the cutoff condition for a given transistor, you set IC equal to 0 to set the stuff going into to figure out the condition when the transistor goes into saturation. You set VCB, or when figure out when for what value of input amplitude the drain the collector will become equal to the base potential, and therefore that will give you one limit. So, for each transistor again you will have one limit, and if you have 100 transistors you will have 100 limits. You have to find the minimum of all the minima that you have found. Okay. Now, if you have an NPN transistor, you know, we said that if you just had NMOS transistors only, then the scope for design is limited, right. So, in that respect, the PMOS transistor was greatly helpful because its characteristic is complementary. Likewise, you know, it's not surprising that you know, if you had an NPN device, there exists a complementary device, that's the PNP, and that's very fortunate because we can do things with NPN and PNP transistors put together, which you could not do with any single time, right. So, basically the PNP also, again you can see that the logic behind drawing the symbols is also very clear. The arrow is always drawn in the direction of flow of current, of the total current, not the incremental current, right. The incremental current could be flowing in the opposite direction, but the total current flows in this direction. So, this is the emitter, this is the base, and this is the collector, and just like how an NMOS, an NMOS circuit can be turned into a PMOS circuit. All we do is basically, you know, first set VDD to minus VDD, right, then add VDD to all nodes. Likewise, you know, to convert a NPN circuit into a PNP1, you change VDD to minus VDD, and we do not like negative potential. So, we add VDD to all nodes, and of course, we do not like currents flowing from the bottom of the page to the top of the page. So, you basically, rather than turn the page or turn your head, you basically you draw the emitters of the PMOS the PNP transistors on the top, and then they flow. Okay. So, now that all of this is, you know, very straightforward, and so again cutoff condition for PNP IC is 0, right. What about the saturation condition? When will the PNP transistor enter saturation? Yeah. So, basically just like in the PMOS transistors, where the drain can go one threshold above the gate, in the PNP transistor, the collector can go as high as the base, right. If it goes above the base, then basically you can see that the emitter collector potential is getting crushed, right. If the potential becomes too small between the emitter and collector, then you cannot have a constant current, right. In the limit when VEC is 0, no current can flow because there is no potential difference. So, so again the saturation condition is VB equal to VC. Right, and IC equal to 0 is the cutoff condition. Okay. Now, after we are done with this, the next thing to do is basically the differential pair, right, and the motivation for doing the differential pair in the two-stage op-amp remains exactly the same. So, let me take some simple examples. This is at 10.65 volts. Let us say this is 100K. And like before, we use the active load. Okay, so this is an example of a two-stage op-amp, right, a toy one, but the basic principles are there. And however, there is a difference between something done with MOS transistors and something done with bipolar transistors. What is the input impedance seen here? By the way, what is the current flowing here? 100 microamperes. Okay, and that basically, if you assume all the transistors are identical, this is also 100 microamperes. Let us assume the betas are large, right. So, what is the input resistance looking in here? Let us assume beta is 100 for instance. What is GM of the transistor? 1 by GM is 25 millivolts by 0.1 milliamperes, that is 250 ohms. 250 ohms times 100 is the input impedance. So, that is basically 25 k. Alright. So, if this was a MOS transistor, what would be the input impedance? Infinite, right. So, now the practical problem that comes about is that the second stage actually loads the first stage, and therefore, the the gain of the first stage is going to get reduced, because the output load now is now ROP parallel, what do you call ROP parallel RON parallel 25 k, and in all likelihood the 25 k is probably going to limit the gain. So, what do you suggest we can do? So, basically you want the input impedance to be higher, you want the same voltage, but the input impedance must be higher. So, what control source will you put between these two terminals? And the problem is you want this voltage to come here, but you do not want any current to be drawn there. So, what do you want to put? Oh, in principle you want to put a voltage control voltage source. What is the simplest voltage control voltage source that you know? Common collector. So, will you put an NMOS, NPN common collector or PNP common collector? PNP. So, one way to do this is just do this. Okay. All right. So, this basically the role of this is to increase the input impedance here. That input impedance will increase if this resistor is very large. The input impedance will increase by a factor of beta. So, that is one thing. And now, if you want to compensate Miller compensate the system, what do we do? Yeah, so basically you could add a CC here. Okay, all right, and so basically this is the and it is very straightforward to. So, let us say this is I don't know 10 puff. So, what is the unity gain frequency? For bipolar transistor, this is very easy to do. What is the current flowing in each of these transistors? 50 microamperes. So, what is the GM of the first stage? 50 microamperes divided by 25. Yeah. So, basically that is basically 2 millisiemens, right, so which is basically 1 over 500 ohms, correct. So, the unity gain frequency omega u is nothing but GM by CC, which is 1 over 500 times 10 puff, correct, which is 200 mega radian per second. Okay. So, that is you divide by 6 roughly to get the unity gain bandwidth in megahertz. Okay. Does that make sense, people? Okay. So, as you can see, it's very straightforward to obtain by simply looking at the picture. You should be able to compute what the unity gain bandwidth of the amplifier is.